Right now, somewhere in our galaxy, a planet is drifting through interstellar space completely alone. No sunrise, no sunset, no parent star, just endless darkness carrying its own heat through the void. Astronomers once thought planets like that were impossible. They were wrong. Since the first world beyond our solar system was confirmed, scientists have discovered thousands more. And instead of making the universe simpler, every new catalog seems to uncover another planet that should not exist. There is a world so hot that molecules are ripped apart before they can survive. Another is slowly being torn to pieces by the gravity of its own star, losing unimaginable amounts of material every year. One appears to be the exposed core of a giant planet after its entire atmosphere somehow vanished. Another formed so far from its star that the leading theories of planetary formation struggle to explain how it ever came to be. And somewhere beyond them all is a planet made largely of crystallized carbon, orbiting the dead remains of a star that no longer shines. Every one of these worlds has been observed, measured, and confirmed. None of them belongs in the neat picture of planetary science we once believed we understood. The more astronomers search the galaxy, the more they encounter planets that seem determined to ignore the rules that were supposed to create them. If reality can produce worlds like these, what else is still waiting to be found? A like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. The story begins with the lonely world that travels through the galaxy without a star to call its own. Long before we can imagine setting foot on these distant worlds, we have already learned to read them. That may sound impossible at first, because every planet in this journey lies so far away that no spacecraft built today, or likely within our lifetimes, could ever arrive there. Even so, you and we already know their sizes, their temperatures, the gases surrounding them, and in remarkable cases, the weather unfolding above skies we will never see directly. The first clue comes from light itself. When a planet passes across the face of its host star, a tiny fraction of that starlight briefly disappears. This event is called a transit, meaning the planet crosses our line of sight. The Kepler Space Telescope spent 9 years watching more than 150,000 stars, searching for brightness changes as small as 1/100th of 1%. Those almost imperceptible dips repeated with dependable timing, allowing astronomers to recognize planets that remained completely invisible in every ordinary photograph. Light alone tells only part of the story. Every planet also pulls on its star through gravity, creating a gentle back and forth motion known as radial velocity. Instead of watching the planet, astronomers measure the star's tiny wobble by examining subtle shifts within its light. When this measurement is combined with transit observations, the planet's size and mass emerge together. From those values comes density, and density offers our first reliable glimpse into whether a distant world is rocky, rich in gas, or something stranger still. Another layer of information appears during the same transit. A small portion of the star's light passes through the planet's atmosphere before continuing toward Earth. Different gases absorb different colors of light, leaving behind distinctive patterns within the spectrum. A spectrum is simply light separated into its individual wavelengths, much like sunlight spread into a rainbow. Those missing patterns become a chemical fingerprint, revealing substances that cannot otherwise be observed across such staggering distances. This technique is why we can identify vaporized metals, exotic clouds, and even the ingredients of rainfall on worlds orbiting other stars. The James Webb Space Telescope expanded this ability dramatically. Launched in December of 2021 and beginning scientific operations in July of 2022, it carries a primary mirror more than 21 feet across. Its extraordinary sensitivity to infrared light allows it to detect faint atmospheric signatures from planets hundreds of light years away, reaching a level of precision that earlier observatories could not achieve. Perhaps the most important word throughout this documentary is confirmed. In astronomy, confirmation does not mean a single exciting observation. It means independent teams, different instruments, separate analyses, and repeated evidence all converging on the same conclusion. That careful process gives us confidence that these distant worlds are not imagined. They are real places, revealed through light that has traveled across the galaxy until it finally reached us. The world we have been circling toward is called WASP 76b. It orbits a star approximately 640 light years away in the constellation Pisces, and astronomers first identified it in the year 2016. 4 years later, observations revealed something that had previously belonged only to speculation. This distant planet truly experiences iron rain. Its dayside reaches approximately 4,350 degrees Fahrenheit. At that temperature, iron cannot remain a familiar metal. It does not gather into solid ground or glowing pools. The intense heat tears it free into vapor, filling the upper atmosphere with gaseous iron that rises alongside other superheated materials. WASP 76b is tidally locked, meaning one hemisphere always faces its star, while the opposite hemisphere remains turned away. You could stand in one location forever and never witness a sunrise or sunset. The same face receives relentless stellar energy, while the far side exists beneath permanent darkness, creating one of the strongest atmospheric contrasts ever measured on an exoplanet. Those opposing conditions drive extraordinary winds. High above the planet, streams of gas race across the globe at roughly 11,000 miles per hour, carrying vaporized iron away from the blazing hemisphere. As that material reaches the cooler side, the temperature finally falls beneath the point where iron can remain suspended as gas. The change is enough to trigger condensation. What forms next is unlike any weather on Earth. Tiny droplets of liquid iron gather within the atmosphere and descend through the darkness. There are no drifting snowflakes or frozen crystals. Instead, molten metal falls from the sky in an endless planetary cycle that has likely continued for millions of years. Astronomers confirmed this remarkable process using the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations mounted on the Very Large Telescope in Chile. Rather than photographing falling droplets directly, researchers studied the planet's spectrum, the distinctive pattern of light absorbed by different elements. Iron appeared clearly along the morning edge of the atmosphere, where cooler air circulates back toward daylight. The same signature was missing along the evening edge. That uneven distribution showed the movement of iron across the planet and provided compelling evidence that the rainfall follows a preferred direction instead of occurring everywhere at once. This remarkable world belongs to a family known as ultra-hot Jupiters, enormous gas giants believed to have formed much farther from their stars before gradually migrating inward over immense spans of time. Its current orbit places it in an environment that reshaped every layer of its atmosphere into something unfamiliar. For us, weather is temporary. Storms arrive, weaken, and pass away. On WASP 76b, the iron rain is simply the climate itself, a permanent cycle written into the planet's structure, continuing beneath a sky no telescope has yet been able to see through in full detail. Imagine a place where the familiar chemistry of planets simply cannot survive, We usually think of atmospheres as mixtures of stable gases, carrying clouds, storms, and recognizable molecules. Around Kelt 9b, those assumptions dissolve under conditions so intense that the building blocks of ordinary planetary weather are pulled apart before they can settle into anything familiar. This extraordinary world lies approximately 670 light years away in the constellation Cygnus. Astronomers announced its discovery in the year 2017, revealing a gas giant orbiting one of the hottest known stars to host a planet. Its day side reaches roughly 7,800 degrees Fahrenheit. For perspective, the visible surface of our own sun measures about 10,000 degrees Fahrenheit. Kelt 9b is therefore hotter than most stars scattered throughout the Milky Way. At such temperatures, molecules cannot remain intact. Water separates into individual atoms. Carbon dioxide cannot survive as a complete compound. Methane and ammonia meet the same fate. Instead of familiar gases drifting through the atmosphere, the heat strips matter into its simpler components, creating an environment where ordinary atmospheric chemistry gives way to something far more extreme. Spectroscopic observations made during the year 2018 revealed another remarkable detail. Iron and titanium exist high above the planet as vapor suspended within the atmosphere itself. Spectroscopy, the study of how matter absorbs specific colors of light, uncovered their unmistakable signatures. These are the same heavy elements that help build the interiors of rocky worlds, yet here they drift overhead as heated gas. The planet circles its host star at a distance of only about 2,100,000 miles. One complete orbit lasts just 1 and 48 Earth days. From that astonishing proximity comes an overwhelming flood of ultraviolet radiation. Kelt 9, the host star, belongs to a class of exceptionally hot stars known as Type A stars. Every square inch of Kelt 9b receives roughly 44,000 times more stellar radiation than Earth receives from the Sunday. Even the hemisphere turned away from the star offers little relief. Temperatures there still exceed 5,400 degrees Fahrenheit. Across the entire planet, heat dominates every process. There is no region where conventional clouds can gather or familiar atmospheric cycles can become established. Every layer remains trapped within conditions that continually reshape its chemistry. You and we are also watching this planet gradually disappear. Powerful radiation drives atmospheric material away into surrounding space at a rate of roughly 10 million tons every second. The escaping gas stretches behind the planet as it races around its star, forming an extended tail resembling that of a comet. Each orbit carries away more of the atmosphere, slowly reducing the planet's mass through a process unfolding before modern telescopes. Kelt 9b reminds us that heat alone can transform a world beyond recognition. Yet even this relentless erosion follows the predictable consequences of extreme radiation. Elsewhere in the galaxy, another planet faces a different fate altogether, one written by gravity itself, as its own star steadily pulls it apart over millions of years. Gravity can shape worlds just as completely as heat. Across the galaxy, one planet demonstrates this with extraordinary clarity, offering us a view of destruction unfolding through forces that govern every orbit in the universe. Its name is WASP 12b, and unlike a sudden collision or explosive catastrophe, its end arrives through an unbroken process that has continued for ages. This gas giant lies approximately 1,400 light-years away in the constellation Auriga. Astronomers confirmed its discovery during the year 2008. It circles its host star from only about 2,100,000 miles away, completing an entire year in just over 26 Earth hours. Such an orbit places the planet among the closest known companions to any ordinary star. At that distance, gravity behaves very differently from what we experience within our own solar system. The same force that raises ocean tides on Earth also stretches entire planets when the difference in gravitational pull becomes great enough. Astronomers call these tidal forces. On WASP 12b, they are so intense that the planet has been measurably distorted. Instead of remaining almost perfectly round, it has been drawn into an elongated shape resembling an enormous egg. The reason lies in an invisible boundary surrounding every orbiting object. This limit is known as the Roche lobe, the region where a body's own gravity can continue holding its material against the attraction of whatever it circles. Once part of a planet extends beyond that boundary, its outer layers are no longer securely bound. They begin responding more strongly to the star than to the planet itself. That is exactly what has happened here. Gas from the upper atmosphere streams away from the planet in a long, curved flow, gradually crossing the gap between world and star. Rather than dispersing into empty space, this escaping material follows gravity inward, becoming an accretion stream, a steady transfer of matter from one object to another. Observations from the Hubble Space Telescope confirmed this remarkable exchange through ultraviolet measurements. Ultraviolet light occupies wavelengths beyond human vision and is especially useful for tracing hot gases surrounding stars and planets. Those observations revealed a broad cloud of absorbing material enveloping both bodies, demonstrating that WASP 12b is losing approximately 189 quintillion tons of matter every year. Its host star does not simply scatter that material. It gathers much of the escaping gas into a surrounding disk before gradually drawing it inward. In a very real sense, the planet has become nourishment for the star it orbits. Every completed orbit leaves it slightly diminished, surrendering another portion of itself to the gravitational pull it can no longer resist. Current estimates suggest this process will continue for somewhere between 3 million and 10 million more years before the planet is completely consumed. Against the age of the universe, that interval is remarkably brief. You and we are witnessing a planetary death already underway, recorded through light that crossed more than 1,000 light years before reaching our telescopes, revealing a world whose final chapter has already begun. Some discoveries challenge our understanding through violence. Others do something more unsettling. They simply exist. Kepler 78b belongs to that second category, a rocky planet whose very presence forces astronomers to reconsider how planetary systems evolve. We can describe what it is with remarkable confidence, yet explaining how it arrived there remains one of the enduring puzzles in exoplanet science. Located approximately 400 light years away in the constellation Cygnus, Kepler 78b was confirmed during the year 2013. It measures about 1 1/5 times Earth's radius and contains roughly 1 7/10 times Earth's mass. Those measurements reveal a dense, rocky world with an iron-rich interior and a silicate mantle, making its overall composition surprisingly similar to our own planet, despite the radically different environment it inhabits. Its orbit is astonishingly compact. One complete year lasts only 8½ hours, shorter than a typical work shift on Earth. The planet circles its host star from a distance of roughly 550,000 miles. Before this discovery, few astronomers believed a rocky world could survive in such proximity for any meaningful length of time. The puzzle begins when we look backward through the history of the star itself. Earlier in its life, the star would have been physically larger than it is today. Calculations indicate that Kepler 78b now occupies a region that would once have fallen within the star's outer envelope. A rocky planet cannot form inside a star, according to any accepted model of planetary formation. That leaves another possibility. It may have formed much farther away before migrating inward across the system. Yet that explanation introduces another difficulty. Existing migration models predict that a rocky planet traveling this close should continue losing orbital energy until it eventually plunges into its star. Stable survival at this distance remains difficult to reproduce through present theories. The Discovery team acknowledged this uncertainty directly, describing the world in their published research as an enigma, a problem whose solution had not yet emerged from the available evidence. The planet's dayside offers another remarkable contrast with Earth. Surface temperatures approach 4,000 degrees Fahrenheit, leaving the rocky crust unable to remain solid across much of the illuminated hemisphere. Instead, vast regions are believed to exist as molten rock, forming an immense ocean of glowing silicate material beneath the relentless heat of the nearby star. Even though its present orbit remains difficult to explain, Kepler 78b will not remain there forever. Tidal interactions between the planet and its host star gradually drain orbital energy, causing the world to spiral inward over immense spans of time. Current estimates suggest it will disappear into the star in approximately 3 billion years. You and we therefore encounter an unusual combination of certainty and mystery. Astronomers understand how this planet is expected to end, yet its beginning remains unresolved. Unlike the previous world, whose destruction followed predictions already established by gravitational theory, Kepler 78b continues to exist in a place where our best models still struggle to explain why it survives at all. There are discoveries that surprise astronomers, and there are discoveries that expose something previously hidden. TOI 849b belongs to the second group. Instead of revealing a completely unfamiliar kind of planet, it appears to have uncovered the interior of one we thought we already understood, leaving its deepest structure exposed to open space. This remarkable world lies approximately 730 light-years away and was identified through observations from the Transiting Exoplanet Survey satellite, with its discovery published during the year 2020. At first glance, its size seems ordinary for a distant giant planet. It measures roughly 3.5 times Earth's diameter, placing it close to Neptune in overall dimensions. The measurement that changed everything, however, was its mass. TOI 849b contains approximately 40 times Earth's mass. According to well-established models of planetary formation, a body this massive should have gathered enormous quantities of hydrogen and helium, while the young planetary system still contained abundant gas. Those light elements should have produced a thick atmosphere similar to the giant envelopes surrounding Jupiter or Neptune. Astronomers expected a gas giant. Instead, they found almost none of that atmosphere remaining. The planet is extraordinarily dense, with a density comparable to Earth's despite its much larger size. Density tells us how much matter is packed into a given volume, making it one of the most useful clues to a planet's internal structure. In this case, the numbers point toward an object composed almost entirely of heavy material, with very little lightweight gas surrounding it. How could such a world come to exist? One explanation proposes that TOI 849b began its life as a conventional gas giant. Over billions of years, relentless radiation from its nearby star may have stripped away nearly the entire atmosphere through a process known as photoevaporation, where energetic stellar light heats gas until it escapes into space. What remains today would be the massive core that once lay buried beneath a vast envelope. Another possibility reaches even farther back into the planet's formation. Perhaps the surrounding cloud of gas had already become depleted before the growing core reached its enormous size. The planet accumulated heavy material successfully, but never found enough hydrogen and helium to complete its expected transformation into a giant gaseous world. Its present orbit lends support to the first explanation. TOI 849b circles its host star once every 18 and 2/5 hours, placing it deep within a region where intense stellar radiation steadily erodes planetary atmospheres. Either history remains extraordinary, and current observations cannot yet distinguish between them with complete certainty. For you and me, the significance extends beyond this single object. TOI 849b represents the first confirmed exposed planetary core ever studied in detail. We cannot peel away the outer layers of Neptune or Uranus to inspect their hidden interiors. Nature appears to have performed that experiment elsewhere, leaving behind a world turned almost inside out, offering a direct glimpse into a planetary structure that normally remains concealed beneath immense layers of gas. Sometimes the mystery is not what a planet is made of, or what its weather is doing. Sometimes the mystery begins with a much simpler question. Why is it there at all? GJ 504b presents exactly that challenge, occupying a location where one of astronomy's most successful theories struggles to explain its existence. This distant giant resides approximately 57 light years away in the constellation Virgo. It was announced during the year 2013 through one of the rarest achievements in exoplanet research, direct imaging. Rather than inferring the planet from changes in starlight or stellar motion, astronomers captured it as its own faint point of light, separated from the glare of its host star. Its orbit immediately drew attention. GJ 500 4b circles at roughly 43 and 1/2 astronomical units from its star. An astronomical unit is the average distance between Earth and the Sunday. Neptune, the outermost major planet in our own solar system, travels at only 30 astronomical units. GJ 504b lies substantially farther from its star than Neptune does from ours, in a region where conventional models predict planet building becomes remarkably inefficient. The planet itself contains approximately 3 to 4 times the mass of Jupiter. According to the dominant explanation for giant planet formation, known as the core accretion model, a solid, rocky core gradually grows by gathering surrounding material. Once that core becomes massive enough, it rapidly attracts hydrogen and helium, forming a gas giant. The farther a forming planet lies from its star, the thinner and colder the surrounding disk becomes. Eventually, there is too little material available for the core to grow efficiently. By that reasoning, a world as massive as GJ 504b should never have assembled so far from its parent star. Astronomers therefore considered another possibility. A process called disk instability suggests that portions of a young stellar disk can become gravitationally unstable and collapse directly into giant planets without first constructing a large rocky core. The idea has existed for decades, yet observations have provided only limited opportunities to test it. GJ 504b has become one of the strongest candidates for this alternative pathway. Even so, it does not prove the theory. It simply remains an object that refuses to fit comfortably within the standard picture. Direct images revealed another unexpected feature. The planet appears with a striking pink and magenta glow. This is not the color of a solid surface. Instead, it is heat escaping from the planet itself. Although the surrounding system formed approximately 160 million years ago, GJ 504b still retains enough leftover warmth from its birth to radiate at roughly 880 degrees Fahrenheit. Its host star closely resembles our Sun in both mass and temperature. If a comparable planet existed within our own solar system, it would drift far beyond the familiar planetary region, glowing faintly through the cold darkness, while continuing to challenge the assumptions that first brought it into view. Among all the worlds astronomers have confirmed, few possess a history as improbable as this one. Before we even consider what it is made of, we have to consider what it orbits. PSR J 1719-1438 b circles a pulsar, the collapsed core of a massive star that ended its life in a supernova explosion. Located approximately 4,000 light-years away in the constellation Serpens, this extraordinary system was announced during the year 2011. A pulsar is a neutron star rotating at tremendous speed while emitting narrow beams of radio waves from its magnetic poles. As those beams sweep across Earth, they arrive with astonishing regularity, much like the beam from a rotating lighthouse. The pulsar in this system completes roughly 10,000 rotations every minute, making it one of the most precise natural clocks ever observed. The planet itself almost certainly began as something very different. Evidence suggests it was once a white dwarf, another type of stellar remnant formed when a smaller star exhausts its nuclear fuel. Over billions of years, the pulsar's intense gravity drew material away from that companion through a process called accretion, the gradual transfer of matter from one object to another. Hydrogen and helium disappeared first, steadily feeding the pulsar while exposing the dense interior that had once been hidden beneath lighter outer layers. What remained was largely carbon and oxygen compressed under extraordinary pressure. Inside such an environment, carbon atoms naturally arrange themselves into an extremely rigid crystal structure. On Earth, we recognize that arrangement as diamond. Current models therefore indicate that PSR J 1719-1438b is composed predominantly of crystallized carbon, making it one of the most unusual planetary objects ever identified. Its physical properties reinforce that conclusion. The planet contains slightly more mass than Jupiter, yet its density is approximately 23 times greater than that of water. Such an immense density cannot be explained by an ordinary gas giant. Instead, it points toward an object formed from intensely compressed stellar material, preserving the exposed heart of what was once an entirely different kind of celestial body. The orbit is equally remarkable. One complete revolution requires only 2 1/5 hours, making it the fastest confirmed planetary orbit known at the time of its discovery. The planet circles only about 373,000 miles from the pulsar, slightly closer than the average distance separating Earth from the Moon. At that range, the collapsed star would dominate the sky, releasing relentless bursts of radio waves, powerful X-rays, and gamma rays with every rapid rotation. You and we are therefore looking at far more than an unusual planet. We are looking at the surviving core of a former star, transformed by billions of years of gravitational interaction into an object whose composition follows naturally from physics, yet still feels almost impossible to imagine. It remains a crystalline remnant circling a collapsed stellar core, preserving within one system an entire sequence of stellar evolution written across unimaginable spans of time. Darkness is usually something we notice by the absence of light. TRES 2b turns that expectation inside out. This distant planet does receive abundant starlight, yet it gives almost none of it back. Instead of shining against the blackness of space, it absorbs nearly everything that reaches its atmosphere, becoming one of the least reflective worlds ever confirmed. The planet orbits approximately 750 light years away in the constellation Draco and was discovered during the year 2006. Astronomers describe its reflectivity using a measurement called albedo, which represents the fraction of incoming light a surface or atmosphere sends back into space. Earth reflects roughly 30% of the sunlight that reaches it. Jupiter reflects about 52%. TRES 2b reflects less than 1%, absorbing well over 99% of the light falling upon it. Such extraordinary darkness places it beyond familiar comparisons. Coal reflects more light, black acrylic paint reflects more light. Even the darkest naturally occurring materials measured on Earth return more light than this planet does. From great distances, trees 2b becomes remarkably difficult to distinguish because almost no visible light escapes its atmosphere and travels back toward an observer. Astronomers have searched for the cause with considerable care. The upper atmosphere appears to contain vaporized sodium and potassium, both capable of absorbing particular wavelengths of light. Titanium oxide has also been proposed as another important contributor because it is especially effective at trapping incoming radiation. Yet no single explanation reproduces the extreme measurements. Current atmospheric models consistently predict a world that should appear brighter than the one telescopes actually observe. The planet is not completely invisible. It generates a faint reddish glow from its own internal heat, similar to the color produced by metal as it gradually cools after intense heating. That glow exists primarily beyond the range of normal human vision, making the world appear almost completely black despite continuously releasing thermal energy into surrounding space. TRES 2b circles its host star from approximately 3 million miles away, completing a rapid orbit while enduring dayside temperatures approaching 1,800 degrees Fahrenheit. Under such conditions, many atmospheric models predict the formation of reflective, high-altitude condensates, tiny suspended particles capable of scattering incoming light. Those expected reflective layers appear to be absent, leaving the atmosphere free to absorb far more radiation than anticipated. For you and me, this unusual darkness represents more than an interesting visual detail. Albedo influences nearly every calculation astronomers make about a planetary atmosphere, a world that absorbs almost all incoming energy experiences, different heating patterns, different circulation systems, different rates of atmospheric escape, and different long term evolution than one reflecting a substantial fraction of its starlight. TRES 2b therefore became an important challenge for atmospheric science, reminding researchers that even seemingly straightforward properties like brightness can reshape our understanding of how distant planets behave under extreme conditions. Temperature alone never tells the whole story of a planet. To understand a distant world, we also have to ask what happens beneath its surface, where pressure steadily increases until matter begins behaving in unfamiliar ways. Gliese 436b demonstrates this beautifully, showing us that heat and pressure can create realities that seem impossible when considered separately. This nearby exoplanet lies only about 33 light years away in the constellation Leo, making it one of the closest extreme worlds known beyond our solar system. Astronomers confirmed its discovery during the year 2004. It measures roughly 4 times Earth's radius and contains approximately 21 times Earth's mass, placing it among the Neptune sized planets that occupy a common category throughout our galaxy. Its outer environment appears thoroughly inhospitable to ordinary water. Surface temperatures reach approximately 822 degrees Fahrenheit. Under those conditions, liquid water cannot remain stable. Any exposed water would rapidly become vapor, leaving little reason to imagine ice existing anywhere within the planet. Yet modern interior models point toward exactly that conclusion. Far below the scorching exterior, pressure rises to approximately 2 million times the atmospheric pressure experienced at Earth's surface. At such extraordinary depths, water enters an exotic phase called supersonic water. In this state, oxygen atoms lock themselves into a rigid crystalline structure resembling a solid, while hydrogen ions continue moving freely through that lattice, much like a liquid. The result is a form of matter that behaves as both solid and fluid at the same time. Scientists first produced this unusual material under carefully controlled laboratory conditions before recognizing that nature could create it on an enormous scale inside distant planets. Gliese 436b, therefore, appears to contain a deep interior layer of hot ice, existing beneath an exterior hot enough to vaporize ordinary water almost instantly. Temperature and pressure govern matter independently, allowing both conditions to remain true within different regions of the same world. The atmosphere tells another remarkable story. During the year 2015, observations by the Hubble Space Telescope confirmed that ultraviolet radiation from the host star steadily strips gas away from the planet. Ultraviolet light carries enough energy to break apart atmospheric particles and drive them into surrounding space. Escaping material stretches behind the planet across nearly 1 million miles, creating a vast comet-like tail that follows its orbit. The host star itself belongs to the red dwarf class. Red dwarfs produce far less visible light than stars like our Sun, yet Gliese 436b circles so closely that even this comparatively modest star delivers enough radiation to erode its atmosphere over immense spans of time. The result is a world whose interior preserves one of the strangest forms of water known to physics, while its outer layers slowly stream away into space. For you and me, Gliese 436b offers another reminder that distant planets rarely follow simple expectations. A blazing exterior and an interior filled with supersonic water can coexist within the same object, expanding our understanding of how familiar materials transform when placed under conditions that no ordinary environment on Earth can sustain. A horizon shaped by two suns was once placed firmly within the realm of imagination. For generations, it belonged to paintings, novels, and cinema. Then careful observation revealed that nature had reached the same conclusion long before we ever pictured it. Kepler 16b transformed a familiar work of fiction into an astronomical reality, reminding us that the universe often proves more inventive than expectation. This remarkable planet resides approximately 245 light years away in the constellation Cygnus. Astronomers confirmed its discovery during the year 2011. It became the first verified circumbinary planet, meaning it does not orbit a single star. Instead, it circles two stars together, treating their combined gravity as the center of its long journey through space. Those companion stars differ noticeably from one another. Kepler 16a is an orange dwarf belonging to the K-type classification. Beside it travels Kepler 16b, a smaller red dwarf classified as an M-type star. They revolve around each other every 41 days, constantly changing their positions while remaining gravitationally bound as a pair. Their shared dance forms the central anchor around which the planet travels. Kepler 16b follows a much broader path, orbiting both stars at a distance of approximately 65 million miles. One complete year on this world lasts 229 Earth days. Throughout that orbit, the stars continually shift across the sky because they are moving around each other as the planet moves around both of them. If you could stand within the upper atmosphere of this Saturn-sized giant, sunrise and sunset would rarely appear the same twice. Sometimes the smaller red dwarf would pass directly in front of the brighter orange companion. During those alignments, the sky would dim as one star partially eclipsed the other. At different times, both suns would remain visible together, tracing separate paths before descending below the horizon. Their changing geometry would create an ever-changing pattern of daylight, unlike anything experienced within our own solar system. Many people recognize this image from the fictional world of Tatooine in the Star Wars stories. Kepler 16b demonstrated that such double sunsets are not imaginative inventions. They are genuine astronomical events occurring on a real planet located hundreds of light years from Earth. Despite its memorable sky, the planet itself appears far less welcoming. It measures roughly the size of Saturn, and its temperature remains near negative 100 degrees Fahrenheit. Current evidence indicates a cold gas giant rather than a rocky world capable of supporting life as we presently understand it. Its existence also resolved an important question in planetary science. Earlier theoretical models suggested that planets orbiting two closely spaced stars might eventually experience gravitational disturbances strong enough to disrupt stable orbits. Kepler 16b has remained stable throughout the estimated age of its system, demonstrating that long-lived circumbinary worlds are entirely possible. Since its discovery, astronomers have confirmed more than a dozen additional circumbinary planets, suggesting that binary star systems, which outnumber solitary stars across much of our galaxy, may build planetary families far more often than once imagined. Some planetary systems seem carefully arranged, each world occupying its own orderly place. Kepler 36 offers a different picture. Two neighboring planets repeatedly draw astonishingly close to one another, sharing the same stellar neighborhood while remaining profoundly different in almost every measurable way. Their repeated encounters have become one of the clearest demonstrations that proximity alone does not guarantee similarity. The system lies approximately 1,208 light-years away in the constellation Cygnus. Astronomers confirmed its existence during the year 2012. At its heart are two planets known as Kepler 36b and Kepler 36c. Their orbits bring them within approximately 1,200,000 miles of each other during their closest approaches, an extraordinarily small separation for neighboring planets. To appreciate that distance, consider our own celestial companion. Earth's moon circles at an average distance of roughly 238,855 miles. During conjunction, when the two exoplanets pass nearest one another, they remain separated by only about 5 times that familiar distance. Across the scale of planetary systems, that is remarkably close. Yet similarity ends there. Kepler 36b is a rocky super-Earth with approximately 4.5 times Earth's mass and 1.5 times Earth's radius. Its interior is believed to contain a dense metallic core wrapped within a silicate mantle, giving it characteristics familiar to the rocky worlds of our own system. Travel outward only a short distance and everything changes. Kepler 36c possesses approximately 8 times Earth's mass, but stretches to nearly 3.7 times Earth's radius. That unusually large size reveals an extensive atmosphere rich in lighter volatile materials, producing a swollen world more closely resembling a small gas giant than a rocky planet. Their years pass rapidly. Kepler 36b circles its star every 13.8 days, while Kepler 36c completes an orbit every 16.2 days. Because those orbital periods differ only slightly, the planets gradually catch one another, arriving at their closest alignment approximately every 97 days. Each meeting follows the same dependable celestial rhythm. If you could somehow stand upon Kepler 36b during one of those encounters, the neighboring planet would dominate the heavens. Kepler 36c would appear approximately 2.5 times wider than our own full moon. Its broad atmosphere could reveal sweeping cloud bands and layered structure without requiring any telescope. The greater mystery lies in their origins. Both planets formed from the same protoplanetary disk, the broad rotating cloud of gas and dust surrounding their young star. They emerged from nearly the same region, drawing upon essentially the same reservoir of raw material. Standard models struggle to explain why one became a dense, rocky body while the other retained a thick, gaseous envelope. Their contrasting compositions remain one of the most compelling formation puzzles yet observed. Although their repeated meetings sound perilous, they are remarkably stable. Their paths are maintained through a near orbital resonance, a repeating gravitational relationship that keeps each world from wandering into the other's path. Their mutual gravitational pull subtly alters their motions, allowing astronomers to calculate their masses with exceptional precision while watching two neighboring worlds perform an enduring cosmic negotiation. Not every planet remains loyal to the star that formed it. In the crowded youth of a planetary system, gravity can become surprisingly unforgiving. Massive worlds tug upon smaller neighbors, orbital paths shift, and close encounters accumulate until one final interaction provides enough momentum to break a planet free forever. Once that happens, there is no return journey. The expelled world continues across the galaxy, carrying only the speed it possessed at the instant of its escape. From that moment onward, no sunrise follows, no familiar year passes. Above such a planet, there is no central star to dominate the sky, only the scattered glow of distant suns separated by immense stretches of darkness. It becomes a rogue planet, wandering through interstellar space without belonging to any planetary system. Finding these lonely travelers presents an extraordinary challenge. They emit little visible light, and they rarely pass in front of bright stars from our perspective. Instead, astronomers often depend upon gravitational microlensing, a method that detects how gravity bends the light of a background star as an unseen object briefly passes between that star and Earth. The effect is fleeting, yet it reveals the hidden mass that caused it. Microlensing surveys have produced an astonishing statistical result. There may be more rogue planets drifting through the Milky Way than there are stars themselves, perhaps numbering in the hundreds of billions. Most remain invisible to us, known only through the mathematics of probability and the occasional brief distortion of distant starlight. One remarkable example appeared during the year 2020. The object, designated Optical Gravitational Lensing Experiment 2016, Background Lensing, Gravitational Lensing, Event 1928, possessed a mass comparable to Mars. It produced a microlensing event lasting only about 40 minutes before disappearing from view. That brief interval may represent the discovery of the smallest confirmed rogue planet yet identified. The James Webb Space Telescope revealed another surprise within the Orion Nebula. Astronomers identified free floating planetary mass objects appearing in pairs, orbiting one another instead of any star. Their origin remains uncertain. They could be planets expelled together while somehow preserving their mutual gravitational bond. Another possibility is even more intriguing. They may belong to an entirely new category of object, occupying the uncertain boundary between planets and failed stars. Despite their isolation, some rogue planets may not be completely frozen throughout. A sufficiently massive rocky world retains internal warmth generated by the radioactive decay of naturally occurring elements deep within its interior. This radiogenic heat can persist for billions of years. The same process contributes to maintaining the hidden ocean beneath Europa's icy shell, although Europa also benefits from tidal heating produced by Jupiter. A rogue planet would rely only upon its internal radioactive energy. Yet theoretical studies suggest that, for large enough worlds, subsurface liquid water could remain stable over immense spans of time. These wanderers may pass surprisingly close without announcing themselves. Current estimates suggest that a rogue planet enters a region comparable to Neptune's orbital distance from our Sun approximately once every 10,000 years. It crosses the outer reaches of our neighborhood without settling into orbit, continuing onward through the galaxy before anyone has an opportunity to notice its passing. After so many worlds, defined by crushing heat, impossible chemistry, or endless isolation, it is natural to wonder whether any confirmed planet has come meaningfully close to resembling our own. Kepler 442b has become one of the strongest candidates, not because it has been proven to host life, but because it satisfies an unusual number of measurable conditions that resemble those of Earth. Even so, its greatest lesson may be the importance of distinguishing possibility from certainty. This planet lies approximately 1,194 light-years away in the constellation Lyra. Astronomers announced its discovery during the year 2015. Among the many ways researchers compare distant worlds, one of the most widely discussed is the Earth Similarity Index. This mathematical scale evaluates a planet's size, density, orbital characteristics, and the amount of stellar energy it receives. A perfect match to Earth would receive a score of 1. Kepler 442b achieves a score of 0.84. That places it among the highest scoring confirmed exoplanets ever identified. For comparison, Mars reaches approximately 0.64, while Venus scores roughly 0.44. The comparison does not declare Kepler 442b to be another Earth. Instead, it tells us that its measurable geometry resembles our own world more closely than almost any other planet currently confirmed. Its parent star also deserves attention. Kepler 442 is a K-type orange dwarf, slightly smaller and cooler than our Sunday. Stars of this class burn their nuclear fuel much more gradually, remaining stable for approximately 20 billion to 70 billion years. By comparison, our Sun is expected to shine for roughly 10 billion years. A potentially habitable planet orbiting such a long lived star could enjoy vastly more time for biological evolution, assuming suitable conditions ever emerge. One complete orbit requires 112 Earth days. Although that year is much shorter than ours, the planet still occupies the star's habitable zone because the orange dwarf radiates less energy. Current estimates indicate that Kepler 442b receives approximately 70% of the stellar energy Earth receives from the Sunday. That amount falls comfortably within the range where liquid water could exist under favorable atmospheric conditions. The planet itself appears somewhat larger than Earth, measuring approximately 1 1/3 times Earth's radius. If it is predominantly rocky, as current evidence suggests, its stronger gravity could shape everything from atmospheric retention to mountain height and ocean circulation. Yet nearly every important detail remains unknown. We do not know whether an atmosphere exists. We cannot confirm oceans, continents, plate tectonics, a protective magnetic field, or even whether the planet always keeps one face toward its star. The Earth Similarity Index measures observable physical parameters. It does not reveal living landscapes or breathable skies. Its host star is estimated to be approximately 2 9/10 billion years old, considerably younger than our Sun's current age of 4 6/10 billion years. If Earth's biological history provides any meaningful comparison, then Kepler 442b may still be in an earlier chapter. What makes this world remarkable is not that it has become another home, but that it satisfies more known prerequisites for habitability at the same time than almost any confirmed planet yet discovered, while reminding us how much remains beyond our reach. Some discoveries become famous for what they reveal. Others become equally important for what they force us to reconsider. Few exoplanets illustrate that difference more clearly than 55 Cancri e, a nearby super-Earth whose changing story has become one of astronomy's best examples of science refining itself as better evidence arrives. Located approximately 40 light-years away in the constellation Cancer, 55 Cancri e was discovered during the year 2004. The planet measures roughly twice Earth's diameter and contains approximately 8 6/10 times Earth's mass. It circles its parent star once every 17 7/10 hours, remaining so close that one hemisphere receives an unrelenting flood of stellar energy. Any familiar landscape would disappear beneath conditions unlike anything found in our own planetary neighborhood. During the year 2012, a peer-reviewed study examined the chemical composition of the host star. Based on the available spectroscopic measurements, which analyze starlight to determine the elements present, researchers concluded that the star might contain an unusually high ratio of carbon compared with oxygen. If the planet formed from that same material, its deep interior could also be rich in carbon. Under immense pressure, carbon naturally crystallizes into diamond. Headlines around the world soon described 55 Cancri e as a diamond planet. It was an exciting possibility. It was also a hypothesis awaiting stronger evidence. Only 2 years later, improved spectroscopic observations provided a clearer measurement of the host star's chemistry. The revised analysis lowered the estimated carbon abundance significantly. Without such an extreme carbon-rich environment, the argument for a diamond-dominated interior weakened substantially. Since then, additional studies have not restored the original interpretation. As new observations accumulated, the picture shifted towards something different, and perhaps even more remarkable. Current evidence suggests that 55 Cancri e is more likely a rocky world dominated by silicate minerals the same broad family of materials that forms much of Earth's crust and mantle. Yet its surface bears little resemblance to our planet. Daytime temperatures rise to approximately 4,400 degrees Fahrenheit, exceeding the melting point of most common silicate rock. Instead of mountains and valleys, the dayside may support an immense ocean of molten stone stretching across the illuminated hemisphere. Conditions may differ dramatically after sunset. As temperatures fall across the night side, some of that vaporized rock could condense and descend once again. Rather than water cycling through clouds and rain, this world may experience a circulation of molten minerals rising into the atmosphere before returning to the surface as liquid rock. The James Webb Space Telescope added another chapter during the year 2023. Measurements of the planet's thermal emission indicated that 55 Cancri E may possess a changing atmosphere containing volatile substances, materials that evaporate readily under planetary conditions, including carbon dioxide or related gases. The atmosphere appears more substantial than that of an exposed bare rock, yet far less extensive than earlier ideas imagined. As you follow the evidence through time, the real achievement becomes unmistakable. The universe did not become less extraordinary when the diamond interpretation faded. Instead, our understanding became more accurate. 55 Cancri reminds us that careful observation is strongest when it welcomes revision, allowing remarkable worlds to become known for what they truly are, rather than for what we first hoped they might be. Some worlds are remarkable because of their appearance, others because of their physics. One planet stands apart simply because it has endured almost the entire history of the cosmos. Formally designated Pulsar Bravo 1620-26 Bravo, and more commonly known as Methuselah, this ancient world resides approximately 12,400 light years away, within the globular cluster Messier 4, deep in the constellation Scorpius. Astronomers confirmed its existence during the year 2003 through a careful combination of pulsar timing and measurements from the Hubble Space Telescope. Pulsar timing measures the astonishingly regular radio pulses emitted by a rapidly spinning neutron star. Tiny deviations in those pulses reveal the gravitational influence of unseen companions. Together with precise positional observations, those signals uncovered one of the oldest confirmed planets ever found. Its estimated age is approximately 12 and 7/10 billion years. Place that beside the universe itself, now estimated at approximately 13 and 8/10 billion years old, and the scale becomes remarkable. This planet formed less than 1 billion years after the Big Bang, long before our sun ignited, before Earth existed, before the raw ingredients of our own solar system had gathered into a single cloud. Methuselah was already completing orbit after orbit. The system itself is unlike almost anything we have encountered. Rather than circling a conventional star, the planet travels around two stellar remnants. One is a millisecond pulsar, a neutron star spinning hundreds of times each second after surviving a supernova explosion. The other is a white dwarf, the dense core left behind after a sun-like star exhausted its nuclear fuel. These remnants orbit one another while the planet circles, both from a distance of approximately 23 astronomical units. You might expect such an environment to prevent planets from existing at all. That expectation once guided much of planetary formation theory. Messier 4 is a globular cluster, an ancient spherical gathering of hundreds of thousands of stars packed far more closely together than those surrounding our own Sunday. Frequent gravitational encounters were thought likely to disrupt forming planetary systems before they could become stable. Methuselah challenged that assumption. Its discovery demonstrated that planets can arise even within these crowded stellar neighborhoods. Somehow, despite billions of years of gravitational interactions, this world survived while countless neighboring stars continued their intricate celestial dance. Its exact composition remains uncertain. At such an advanced age and tremendous orbital distance from its compact hosts, the planet likely receives very little heat. Current evidence suggests it is probably a gas giant or ice giant, spending nearly its entire existence beneath profoundly cold conditions that have changed little across billions of years. When we consider Methuselah, another realization gradually emerges. If planets were already forming within the universe's first billion years, then worlds have accompanied cosmic history almost from the beginning. Across those immense spans of time, civilizations may never have appeared, or perhaps they rose and disappeared beyond any possibility of detection. We simply do not know. What we do know is that this ancient planet has witnessed nearly everything the universe has ever become, continuing its patient orbit while entire generations of stars, including our own sun, arrived astonishingly late. At first glance, this world offers one of the most deceptive views in planetary science. From across approximately 64 light years in the constellation Vulpecula, you would see a rich blue sphere suspended against the darkness. It recalls the familiar color of Earth viewed from orbit, inviting the mind toward oceans, clouds, and an atmosphere that scatters sunlight in comforting ways. That resemblance fades the moment we ask what creates the color. Confirmed during the year 2005 and studied extensively in the years that followed, Hotel Delta 189733. Bravo owes its striking appearance to suspended silicate particles. Silicates are minerals built from silicon and oxygen, the same broad family of materials that forms much of Earth's rocks. High above this planet, those minerals condense into microscopic particles of glass. Rather than reflecting from water, the blue light reaching distant telescopes is scattered by countless fragments drifting through the upper atmosphere. Temperatures reshape every layer of this world. The hemisphere facing its star reaches approximately 1,900 degrees Fahrenheit, while the permanent night side remains closer to 1,200 degrees Fahrenheit. That difference of roughly 700 degrees Fahrenheit creates an enormous imbalance in atmospheric energy. Hot gas constantly surges toward cooler regions, while cooler material is drawn back again in a continuous planetary circulation. The resulting winds rank among the fastest ever measured beyond our solar system. Observations indicate speeds approaching approximately 5,400 miles per hour, nearly 7 times the speed of sound in Earth's atmosphere. Imagine standing beneath a sky where every current moves faster than the fastest military aircraft ever built. Now imagine those currents carrying sharp particles of glass instead of dust or water droplets. This is why descriptions of glass rain require careful wording. The atmosphere is not experiencing an occasional storm. It exists in an ongoing cycle where silicate particles condense, fall, become swept sideways by supersonic winds, heat again, and re-enter the circulation. Rain is only one moment within that endless exchange. The atmosphere itself has become the weather, operating without pause under conditions that never allow lasting calm. Astronomers learned even more by observing the planet in infrared wavelengths, a form of light produced by heat rather than visible brightness. Those observations allowed researchers to map the movement of atmospheric temperatures across different regions. For one of the first times beyond our solar system, weather patterns were not merely inferred, they were measured, revealing organized circulation with identifiable direction and structure. You may remember another intensely heated gas giant encountered earlier in our journey. Although both belong to the class known as hot Jupiters, and both remain tidally locked, Hotel Delta 189733, Bravo follows its own atmospheric chemistry. The glass circulating through its skies reflects the abundance of silicate material present there, rather than representing a universal feature shared by every world of this type. Its blue appearance reminds us how easily familiar colors can mislead. Sometimes the universe borrows a palette we recognize, then paints an entirely different reality beneath it, where beauty and violence occupy the very same sky. Every so often, a single observation changes the conversation without changing the conclusion. That distinction matters. Kilo 2-18 Bravo, located approximately 120 light years away in the constellation Leo, has become one of those rare worlds where the questions grew larger, while the answers remained carefully restrained. Discovered during the year 2015, this planet belongs to a class known as sub-Neptunes. These are worlds larger than Earth, yet smaller than Neptune, occupying a size range absent from our own solar system. Kilo 2-18, Bravo measures approximately 2 and 6/10 times Earth's radius and contains approximately 8 and 6/10 times Earth's mass. It circles a red dwarf star every 33 days, remaining within the region where temperatures could allow liquid water under suitable atmospheric conditions. The James Webb Space Telescope brought this planet into sharper focus during the year 2023. By studying the faint starlight filtering through its atmosphere during transit, astronomers identified clear signatures of carbon dioxide and methane. Those molecules fit well with expectations for a hydrogen-rich atmosphere surrounding a sub-Neptune. The observations were significant, yet they aligned comfortably with existing models. One additional signal attracted far greater attention. The data contained a possible indication of dimethyl sulfide, an organic sulfur-bearing molecule. On Earth, dimethyl sulfide is produced almost entirely by marine phytoplankton, microscopic organisms living within the upper layers of the oceans. No confirmed non-biological process has been shown to generate dimethyl sulfide in comparable abundance under natural conditions found on our planet. You might wonder whether that means life has already been discovered. The careful scientific answer is no. The possible detection sits close to the sensitivity limits of the James Webb Space Telescope for this particular molecule. The research team emphasized that the signal remains preliminary and requires additional observations before it can be confirmed or rejected. A measurement near the edge of an instrument's capability deserves attention, yet it also demands extraordinary caution. Kilo 2-18 Bravo is intriguing for another reason as well. Some researchers classify it as a candidate Haitian world. A Haitian planet is a theoretical type of world possessing a hydrogen-rich atmosphere above a vast global ocean. Computer models suggest that the boundary where such an atmosphere meets liquid water could provide temperatures, pressures, and chemical conditions compatible with certain forms of microbial life. Compatible does not mean inhabited. It simply means those environments are not ruled out by current physics and chemistry. That distinction shapes the entire story. Scientists are not claiming life has been found. They are acknowledging that this is the first confirmed exoplanet where a molecule associated almost exclusively with biological activity on Earth, has appeared as a candidate within an atmospheric spectrum. The signal may ultimately disappear under improved observations. It may prove to be an unexpected chemical process unrelated to biology, or it may point towards something genuinely new. For now, we continue watching with patience. The greatest value of Kilo 2-18 Bravo lies in how honestly it reminds us that careful science advances through measured confidence, allowing remarkable possibilities to remain open while demanding evidence strong enough to carry them. Suppose, one evening, a telescope receives light from a distant world that contains a molecule strongly associated with living organisms. Would that be enough to announce life beyond Earth? The careful answer is no. In planetary science, such a discovery marks the opening of an investigation rather than its conclusion. The signal itself is called a biosignature, meaning a chemical or physical feature that could indicate biological activity if every reasonable non biological explanation can first be eliminated. Oxygen provides the classic example. On Earth, nearly all free oxygen in the atmosphere exists because photosynthetic organisms continually release it. Without life replenishing that supply, oxygen would gradually react with rocks and gases until very little remained. Yet nature offers another pathway. Intense ultraviolet radiation can split water vapor into hydrogen and oxygen through a process called photodissociation, where energetic light breaks molecules apart. Hydrogen escapes into space more easily, leaving oxygen behind. A distant atmosphere rich in oxygen therefore raises interest, but it does not settle the question. Methane presents a similar challenge. Countless microorganisms produce methane across Earth's wetlands, sediments, and digestive systems. Volcanoes, chemical reactions between water and hot rock, and other geological processes can also generate methane without biology. Observing methane by itself, therefore, provides an intriguing clue rather than convincing evidence. The situation changes when methane and oxygen appear together. These gases react readily with one another in the presence of sunlight. Left alone, they steadily disappear through ordinary chemistry. On Earth, they coexist only because living systems continuously replace both. Detecting them simultaneously within the atmosphere of another planet would represent a substantially stronger biosignature than finding either gas independently, because maintaining that chemical imbalance requires an ongoing source. Even then, caution remains essential. During the year 2020, astronomers reported a possible detection of phosphine high within the atmosphere of Venus. Phosphine attracted attention because no well-established non-biological process seemed capable of producing the reported amount under Venusian conditions. As additional teams re-examined the observations, confidence in both the detection and the estimated abundance declined. Today, the claim remains contested rather than confirmed, illustrating how extraordinary conclusions demand repeated and independent verification. This broader lesson shapes every modern search for life. No individual molecule serves as an unmistakable biological fingerprint without understanding the surrounding environment. Researchers must evaluate atmospheric chemistry, geological activity, incoming stellar radiation, planetary temperature, pressure, and countless interacting processes before deciding whether biology provides the best explanation. That level of understanding requires complete planetary characterization, a detailed picture of an entire world rather than a single spectral feature. The James Webb Space Telescope has begun that process for several nearby planets, revealing atmospheric compositions with unprecedented precision. Yet even this remarkable observatory represents only an early step. Future missions, including the proposed Habitable Worlds Observatory, are being designed specifically to analyze Earth-sized planets with far greater sensitivity. As our instruments improve, the search becomes steadily less about finding one remarkable molecule and more about assembling an entire planetary story, piece by careful piece, until the evidence can stand securely on its own. There was a time, surprisingly recent, when every planet humanity knew belonged to a single family. Every orbit, every moon, and every atmosphere we had ever studied circled our own Sunday. Beyond that familiar neighborhood, planets remained reasonable speculation rather than established fact. If you had looked toward the stars before the year 1992, you would have found countless possibilities. But the number of confirmed exoplanets was exactly zero. That changed with an unexpected discovery around a pulsar designated as Pulsar B 1257 plus 12. A pulsar is a neutron star that spins with astonishing precision, sending beams of radio waves through space like the sweeping light of a lighthouse. Astronomers noticed tiny irregularities in the timing of those radio pulses. The star itself was behaving almost perfectly, yet something kept tugging on it. Those subtle disturbances revealed three rocky planets, detected through gravity alone. Their light was invisible, but their influence could not remain hidden. Only 3 years later, another assumption gave way. Astronomers confirmed the first planet orbiting a sun-like star, 51 Pegasi b. This world carried roughly half the mass of Jupiter while circling its star every 4.2 days. Before that discovery, many researchers expected giant planets to remain far from their stars, following a pattern similar to our own solar system. Instead, this enormous gas giant raced through an orbit far tighter than anyone had anticipated, demonstrating that planetary systems could organize themselves in ways our local example never suggested. As discoveries accumulated, the Kepler Space Telescope transformed isolated surprises into statistics. Rather than focusing on individual planets, it measured how frequently different kinds of worlds appeared across thousands of stars. One conclusion stood above the rest. Approximately one-fifth of Sun-like stars appear to host at least one Earth-sized planet within the habitable zone, the orbital region where temperatures could allow liquid water under suitable atmospheric conditions. Applied across the Milky Way, that percentage suggests roughly 300 million potentially habitable Earth-sized planets. Another result proved equally remarkable. The most common planets in our galaxy fall between Earth and Neptune in size. These super-Earths and mini-Neptunes dominate the census of known worlds. Yet our own solar system contains no representative of either category. The most typical planetary class in the galaxy has no nearby example for us to examine directly. Viewed from that broader perspective, our own planetary system begins to look somewhat unusual. Many observed systems place their largest planets remarkably close to their host stars. Jupiter, by contrast, occupies a distant orbit at roughly 5.2 astronomical units. Its immense gravity redirects many comets and asteroids that might otherwise enter the inner solar system, contributing to a long period of relative stability that may have helped complex life emerge on Earth over billions of years. Today, the confirmed count has climbed beyond 5,700 exoplanets, and the pace of discovery continues to increase as telescopes become more capable. We now understand that planets are not rare exceptions scattered through the Milky Way. They are among its most ordinary inhabitants, filling the galaxy in numbers that would have seemed almost unimaginable only a generation ago. Long before astronomers confirmed a single planet beyond our solar system, one simple question lingered in scientific conversation. If the universe has existed for billions of years and stars fill every direction we can observe, where is everyone? That question became known as the Fermi paradox, named after physicist Enrico Fermi, who raised it informally in the year 1950, decades before exoplanets transformed astronomy. At the time, the number of confirmed planets beyond our own system remained exactly zero. Today, we know the galaxy very differently. Hundreds of billions of stars populate the Milky Way. Many possess planetary systems, and Earth sized planets with habitable zones appear far more common than early estimates suggested. Two of the greatest uncertainties in the Drake equation, the fraction of stars with planets and the frequency of potentially habitable worlds, shifted from speculation toward observation. Rather than resolving the paradox, those discoveries sharpened it. If suitable worlds are abundant, why has no technological civilization revealed itself with confirmed certainty? One proposed explanation is called the Great Filter. This idea suggests that somewhere between simple chemistry and an advanced civilization capable of crossing interstellar distances lies an extraordinarily improbable step. Perhaps that obstacle already lies behind us, meaning complex life almost never emerges. Or perhaps it still waits ahead, causing civilizations to disappear before spreading through the galaxy. We simply do not know which possibility, if either, reflects reality. Another explanation is the rare Earth hypothesis. Although habitable planets may be widespread, the precise combination of circumstances that shaped Earth could prove exceptionally uncommon. Our large moon helps stabilize Earth's axial tilt over immense spans of time. Jupiter occupies a distant orbit that redirects many incoming comets and asteroids. Plate tectonics continually recycle the surface, while liquid water has persisted for billions of years. Could all those conditions appearing together represent a cosmic rarity rather than an expectation? Some researchers consider the zoo hypothesis. According to this proposal, advanced civilizations may already exist while deliberately avoiding interference with younger societies. Observation without contact would preserve natural development, much as wildlife researchers minimize their influence on the animals they study. It remains an interesting possibility, though there is no evidence confirming such behavior. Others suggest that humanity may simply have arrived early. Heavy elements required for rocky planets accumulated gradually as generations of stars lived and died. Future eras of the galaxy may contain far more mature planetary systems than exist today. If that is true, the greatest age of technological civilizations could still lie billions of years ahead. Every explanation remains unconfirmed. The remarkable fact is that the silence persists. Decades of searches conducted by the Search for Extraterrestrial Intelligence have produced no verified artificial signal from another civilization. That absence is meaningful, yet it must be interpreted carefully. Failing to detect evidence does not demonstrate that nothing exists beyond our reach. It tells us only that, so far, the galaxy has not answered in a way we can confidently recognize. After traveling across worlds of molten rock, diamond interiors, wandering darkness, and skies ruled by more than one sun, it becomes possible to look back at our own planet from a different direction. We often describe Earth as ordinary because it is familiar, yet familiarity can disguise improbability. The conditions that shaped every living thing you have ever known are, by the standards of the planets we continue discovering, remarkably uncommon. Liquid water covers approximately 71% of Earth's surface, with an average depth of about 12,100 feet. More remarkable still, those oceans have remained in liquid form for roughly 3.5 to 4 billion years. Water exists as a liquid only within a relatively narrow range of pressure and temperature. Across the growing catalog of confirmed exoplanets, that balance appears far less common than crushing heat, permanent freezing, or atmospheres too hostile to support long lasting oceans. Another uncommon characteristic lies beneath our feet. Earth is the only confirmed world in our solar system with active plate tectonics. Massive slabs of crust drift slowly across the surface, carrying carbon deep into the mantle before volcanic activity returns it to the atmosphere. This carbon silicate cycle functions as a planetary thermostat, regulating carbon dioxide across immense spans of geological time. Without that process, climate could gradually drift toward conditions resembling the runaway greenhouse environment of Venus. If long term habitability depends on this recycling system, then Earth possesses another rare advantage. Our moon also deserves a second look. Compared with other rocky planets, it is unusually large relative to the world it orbits. Its steady gravitational influence keeps Earth's axial tilt remarkably stable, varying by only about 2 and 2/5 degrees across vast periods. Without that stabilizing presence, simulations suggest the tilt might wander chaotically between approximately 0 and 85 degrees. Such dramatic shifts could transform global climates repeatedly, creating conditions far less favorable for the gradual evolution of complex life. Deep within Earth's interior, molten iron circulates around a solid inner core, generating a magnetic field through a process called the dynamo effect. This invisible shield deflects much of the solar wind, a continuous stream of charged particles flowing outward from the sunday. Mars lost its global magnetic field early in its history, and much of its atmosphere was gradually stripped away afterward. Earth's protective field has endured for at least 3.5 billion years, preserving an atmosphere capable of supporting oceans and life. Even Jupiter may have contributed to this remarkable sequence. Occupying a distant orbit, the giant planet redirects many long period comets and asteroids before they can reach the inner solar system. Although its influence is complex and still actively studied, many researchers conclude that Earth's impact rate over the past 600 million years has likely been lower than it would have been without a Jupiter like companion. None of these circumstances were planned. They emerged from the same universal laws that produced collapsing stars, drifting rogue planets, and worlds wrapped in molten stone. The physics never changed. Only the initial conditions did, and among those countless outcomes, one combination became the place where you and I could ask why it happened at all. Distance has quietly shaped every world we have visited tonight. Each remarkable planet, whether wrapped in molten stone, wandering without a star, or orbiting two suns, exists beyond any journey humanity can presently undertake. Our understanding has expanded dramatically, yet our physical reach has scarcely moved beyond the edge of our own stellar neighborhood. Consider the closest extreme planet we have explored in this documentary. High definition 18973 3b. It lies approximately 64 light years away. A single light year spans about 5.88 trillion miles. Across 64 of them, the separation grows to roughly 376 trillion miles. Numbers of that scale become difficult to picture because they exceed anything encountered in ordinary experience. Voyager 1 remains the most distant human-made object ever launched. Traveling at approximately 38,000 miles per hour, it has spent decades leaving the solar system behind. Even at that remarkable speed, The journey to high definition 189733b would require approximately 1,100,000 years. The nearest confirmed exoplanet, Proxima Centauri b, appears far more accessible at 4.24 light-years away. Yet Voyager 1 would still need roughly 73,000 years to arrive. These are not engineering problems waiting for slightly better rockets. They emerge from the structure of the galaxy itself. Stars form across immense regions of space, separated by distances measured in light years rather than planetary orbits. The vastness is woven into the architecture of the universe, remaining unchanged regardless of our ambitions. Yet something equally remarkable has happened in the opposite direction. Instead of traveling outward, we have learned to let light bring distant worlds to us. The James Webb Space Telescope has demonstrated that starlight passing through an exoplanet's atmosphere carries subtle fingerprints of the gases encountered along the way. A spectrum is light separated into its individual colors, revealing which molecules absorbed specific wavelengths before the light continued across space. By studying those delicate patterns, astronomers identify atmospheric chemistry on planets hundreds of light years away. Think about what that truly means. We cannot touch these worlds, land upon them, or collect a single grain from their surfaces. Even so, we can determine that methane, carbon dioxide, water vapor, and other molecules exist in skies that no spacecraft has ever approached. Detecting atmospheric chemistry on a planet smaller than Neptune from hundreds of light years away ranks among humanity's most astonishing scientific achievements. There are proposals to narrow those distances. The breakthrough starshot concept, introduced in the year 2016, envisions gram-scale spacecraft accelerated by powerful ground-based lasers to 1/5 the speed of light. Such tiny probes could, in principle, reach the Alpha Centauri system in about 20 years. Enormous technical challenges remain unresolved, from surviving collisions with interstellar particles to maintaining the laser beam across extraordinary distances. For everyone alive today, the nearest stars will almost certainly remain beyond direct reach. Yet our ability to understand them continues advancing with remarkable speed. We have entered an era where knowledge travels much farther than we do, carried by ancient light that has crossed the galaxy before finally reaching our instruments. Looking back across this journey, a remarkable pattern begins to emerge. Every extraordinary planet we have explored forced astronomy to reconsider something once treated as dependable. Each discovery widened the map, not by filling in empty spaces, but by revealing that the boundaries themselves had been drawn too narrowly. Kilo Extremely Little Telescope, 9b, challenged the expectation that no planet could become hotter than many stars. Kepler 78b demonstrated that a rocky world could survive astonishingly close to its host star. Transiting Exoplanet Survey Satellite Object of Interest 849b showed that a planet with Neptune's mass could exist after losing nearly all of its thick atmosphere. Gliese 504b appeared so far from its star that prevailing formation models struggled to explain its existence. Pulsar Juliet 1719-1438b rewrote something even more fundamental, proving that planets could orbit stellar remnants instead of ordinary stars. Each discovery arrived with careful skepticism. Observations were checked, calculations repeated, alternative explanations examined. Only after surviving that process did these worlds earn their place in astronomy. Their greatest contribution was never surprise alone. It was the evidence they carried, evidence strong enough to reshape established understanding. For much of modern history, theories of planetary formation successfully explained our own solar system. That success created an understandable assumption. Perhaps other planetary systems resembled ours with only modest variations. The first decades of exoplanet discoveries revealed something profoundly different. Our neighborhood represents one successful arrangement among many, rather than a universal blueprint. When we describe one of these worlds as extreme, we are speaking from our own perspective. The universe does not recognize unusual cases. Gravity acts the same way everywhere. Nuclear fusion follows the same physical laws in every star. Chemistry obeys identical principles across the galaxy. Change the initial conditions, the mass of a forming star, the composition of a collapsing cloud, or the timing of planetary migration, and entirely different worlds emerge without breaking a single law of nature. You can trace the history of planetary science through successive revisions rather than permanent conclusions. Every reliable model began with available evidence, generated predictions, and faced comparison with new observations. Whenever reality refused to fit those predictions, the model expanded. Each revision became broader, more flexible, and ultimately more accurate than the one before. That progression represents science functioning exactly as intended. Only a few decades ago, nearly all of these planets would have belonged to speculation. Today, they belong to observation. Their existence reminds us that discovery rarely narrows the universe. More often, it enlarges it. The catalog grows, the exceptions multiply, and patterns once considered universal become local examples within a much richer cosmic population. What these worlds reveal together is neither disorder nor contradiction. They reveal possibility. Our solar system is one expression of the same physical laws that produced lava oceans, wandering rogue planets, ancient survivors, stripped planetary cores, and worlds whose atmospheres carry molecules across hundreds of light years before reaching our telescopes. The rules never changed. Only our understanding of how many outcomes those rules could produce became far larger than anyone first imagined. A lifetime can be long enough to watch an entire branch of science transform. The sky above humanity has not changed during these decades, yet our understanding of what fills it has expanded at a pace few astronomers expected to witness firsthand. At the beginning of the 1990s, confirmed planets beyond our solar system did not exist in observational astronomy. Researchers strongly suspected they were out there. Planet formation appeared to be a natural consequence of star formation. Even so, confidence is different from confirmation. Until evidence arrives, science leaves room for doubt. That changed in 1992 with an unexpected discovery. Alexander Woljan and Dale Frail identified three planets orbiting the pulsar, designated Pulsar Bravo 1257 plus 12. Their presence was revealed through pulsar timing, a method that measures tiny changes in the arrival of remarkably regular radio pulses. The planets themselves remained invisible. Instead, their gravity disturbed one of the most precise natural clocks in the universe. Curiously, the first confirmed planetary system beyond our own surrounded a dead stellar remnant rather than an ordinary star. Only 3 years later, another assumption gave way. Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. Its year lasted only a little more than 4 Earth days. Giant planets had been expected to remain far from their stars, following the familiar arrangement of our own solar system. Instead, this hot Jupiter occupied an orbit that earlier models had considered highly unlikely. Their discovery earned the Nobel Prize in Physics in 2019, recognizing a breakthrough that permanently changed astronomy. The pace accelerated when the National Aeronautics and Space Administration launched the Kepler Space Telescope in 2009. Its purpose extended beyond finding remarkable individual worlds. Kepler sought statistics. By 2014, the number of confirmed exoplanets had surpassed 1,000. Before the end of 2022, that total exceeded 5,000. Thousands more candidates continue moving through careful verification, each adding another point to an increasingly detailed picture of our galaxy. Think about what that means for generations alive today. Anyone younger than roughly 35 years has spent nearly an entire lifetime in an era when confirmed exoplanets were simply part of accepted scientific knowledge. Yet the extraordinary catalog we explored tonight, lava oceans, stripped planetary cores, rogue wanderers, ancient survivors, and atmospheres carrying carbon dioxide, methane, and other detectable molecules, emerged almost entirely within that same span of years. The momentum has continued rather than fading. During its first years of operation, the James Webb Space Telescope produced atmospheric observations with a depth unimaginable only a short time earlier. Its planned mission extends many years into the future, promising increasingly detailed studies of nearby planetary systems. You may see catalogs containing hundreds of atmospheric profiles, stronger evidence for potentially habitable environments, or perhaps the careful confirmation of a biosignature that survives every alternative explanation. You may also see difficult questions remain unanswered. Either outcome represents progress, because the instruments are finally capable of asking those questions with remarkable precision. After everything we have explored together, the numbers gather into a single remarkable picture: more than 5,700 confirmed planets, atmospheres analyzed across immense reaches of interstellar space, worlds where iron condenses from scorching skies, planets stripped to their rocky hearts, ancient survivors older than our solar system, companions circling dead stars, and systems unlike anything imagined only a few decades ago. Never before has humanity possessed such a detailed portrait of planetary diversity. Yet one question remains exactly where it began. Are we alone? Every confirmed exoplanet has strengthened our understanding of physics, chemistry, and planetary evolution. Each observation reveals how matter behaves under different temperatures, gravities, and stellar environments. Together, they describe an astonishing variety of possible worlds. What they have not yet revealed is confirmed biology. No telescope has detected an unmistakable living ecosystem beyond Earth. No atmospheric spectrum has crossed the threshold from intriguing possibility to established fact. The planet designated K2-18b brought that question into sharper focus than any previous discovery. Observations by the James Webb Space Telescope identified carbon dioxide and methane, along with a tentative indication of dimethyl sulfide, a molecule associated on Earth with living marine organisms. The research team emphasized that this remained a candidate detection requiring additional observations. That careful restraint reflects one of science's greatest strengths. Extraordinary possibilities demand equally extraordinary standards of evidence. What has changed is the landscape surrounding the question. We now know that environments potentially compatible with life are not isolated curiosities. Liquid water may persist beneath frozen surfaces. Stable climates may endure around long-lived stars. Atmospheric chemistry can include ingredients associated with biological processes. Energy sources capable of driving complex reactions appear across many planetary settings. The conditions that seem important for life are no longer confined to a single known world. Whether those conditions regularly produce living organisms remains completely unresolved. You might wonder whether the continuing absence of confirmed evidence should itself be treated as an answer. It should not. The Milky Way spans 100,000 light years. Our searches have examined only a minute fraction of its stars, and only with instruments that have recently become capable of detecting the faintest planetary signals. No confirmed radio transmission from another civilization has been received. No confirmed technosignature has survived independent verification. No confirmed biosignature has yet met the demanding standard required for scientific acceptance. These are meaningful observations, yet they remain observations within a search that has barely begun on a galactic scale. The most accurate answer available today is remarkably simple. We do not know whether life exists beyond Earth. That statement is neither disappointing nor incomplete. It is an honest reflection of the evidence. After one generation transformed the universe from a place with no confirmed exoplanets into one containing thousands of known worlds, the greatest remaining mystery has become more focused rather than more distant. We now understand where to look, what to measure, and which questions deserve the greatest care. The uncertainty has narrowed, even though the answer itself still waits beyond the edge of confirmed knowledge. Long before any telescope gathered their light, these worlds were already following their own histories. The planet called WASP 76b had been carrying rivers of vaporized iron through its atmosphere for millions of years. Pulsar Juliet 1719-1438b had completed uncountable orbits around its pulsar. The ancient world, known as Methuselah, had circled its pair of stellar remnants for approximately 12.7 billion years, beginning its journey when the universe itself was still remarkably young. None of them changed because we noticed them. The Iron Rain did not begin when the Haeckel spectrograph for rocky exoplanets and stable spectroscopic observations instrument resolved evidence for it during 2020. The dense carbon world orbiting a pulsar did not suddenly crystallize when radio timing observations established its remarkable nature. Every measurement represented a moment of recognition rather than creation. Discovery altered our understanding, while the planets themselves continued exactly as they always had. There is something deeply unusual in that realization. Across distances, measured in light years, we acquire knowledge of places we will never visit, places that neither know nor require our existence. The universe offers no performance for an audience. It unfolds according to gravity, nuclear fusion, chemistry, and time, whether anyone is present to witness the outcome or not. Its history stretches across approximately 13.8 billion years. Humanity occupies only a brief interval within that immense chronology. Our observatories, spacecraft, and radio antennas belong to a recent chapter written long after galaxies assembled, stars ignited, and countless planetary systems settled into their enduring motions. Long after every instrument humanity has ever built becomes inactive, those same physical processes will continue shaping new stars and new worlds. Yet this perspective carries another truth that is equally remarkable. We are not separate from what we observe. The iron suspended within the atmosphere of WASP 76b is the same chemical element that allows hemoglobin to transport oxygen through the blood of every person listening tonight. The carbon compressed into extraordinary forms around a pulsar belongs to the same family of atoms that forms the structural framework of proteins, sugars, and deoxyribonucleic acid within every living cell on Earth. The calcium inside distant planets, the silicon inside rocky crusts, and the oxygen filling alien skies all originate from the same cosmic processes that produce the matter composing our own bodies. So when you look outward, the separation is one of distance rather than substance. The telescopes, mirrors, detectors, and computers examining these planets are themselves assembled from elements forged inside ancient stars. The observers and the observed share the same physical origin. The iron rain remains real. The glass storms remain real. The exposed planetary core, the wandering rogue worlds, and the oldest confirmed planet yet discovered all continue to exist at this very moment. They are not stories waiting to be told or ideas waiting to be imagined. They are places following their own histories beneath the same universal laws that also made it possible for a small civilization on one blue planet to notice them at all. Imagine stepping so far beyond our own neighborhood that the sun itself becomes only another ordinary star among countless others. From that immense distance, Earth no longer appears as continents, oceans, or clouds. It becomes a single point of light, carrying every chapter of our history within a beam too small for the eye to separate. In 1990, as Voyager 1 was departing the planetary realm, astronomer Carl Sagan requested that the National Aeronautics and Space Administration turn the spacecraft's camera back toward home. From approximately 3.7 billion miles away, Earth appeared as less than a single pixel, suspended within scattered sunlight. Everything humanity had ever built or remembered occupied that tiny speck. The photograph did not change our planet. It changed the scale through which we understood it. If you stood instead at the distance of HD 189733b, approximately 64 light-years away, Earth would disappear completely behind the overwhelming brilliance of the Sunday. No telescope humanity has constructed today could isolate our world from that glare across such a span. Detecting it would demand an observatory substantially more capable than the James Webb Space Telescope, one able to separate an exceedingly faint planetary glow from the overwhelming light of its parent star. Distance reshapes time as well as vision. From the direction of Kepler 442b, approximately 1,194 light-years away, the light departing Earth at this moment has not yet begun its journey. An observer there would currently receive light that left our planet during approximately the year 830, when medieval kingdoms covered much of Europe, centuries before the printing press, modern science, or any telescope capable of revealing another planetary system. The reverse is equally true for us. Every photon arriving tonight departed its source long ago. Some began traveling before the first steam engine. Others started their passage before written history emerged in many parts of Earth. We never observe the universe in one universal present. Instead, every direction reveals a different moment, assembled into a single sky by the finite speed of light. Viewed from far enough away with sufficiently advanced instruments, Earth would reveal something distinctive. Its atmosphere contains oxygen, methane, water vapor, and ozone at the same time. Together, those gases exist in combinations that challenge purely non-biological explanations. Any civilization capable of measuring that atmospheric spectrum would likely identify our planet as a compelling candidate for life, deserving careful investigation rather than immediate certainty. So far, Earth remains the only confirmed inhabited world known to science. For approximately 2.5 billion years, its atmosphere has carried that chemical message into space. The signal has expanded outward at the speed of light, crossing one stellar neighborhood after another, long before humanity understood what it was broadcasting. Whatever may exist beyond our reach, if anything does, has had ample time to notice that one small point of light has been telling its story all along. No catalog in astronomy remains complete for long. Every confirmed entry represents a moment in an ongoing record, one revised whenever fresh observations survive careful testing. The collection of known exoplanets is growing continuously, shaped by new detections, improved measurements, and atmospheric analyses that refine what earlier generations of instruments could only suggest. If you return to that catalog 10 years from now, it will describe a galaxy richer than the one we recognize today. The James Webb Space Telescope has only begun its scientific life. Its projected mission extends for at least another 20 years, and during that time, it is expected to build atmospheric profiles for hundreds of distant worlds. Light that once appeared featureless is now being separated into detailed spectra, revealing carbon dioxide, methane, water vapor, and many other compounds with a precision that was beyond reach only a few years ago. We are watching a new branch of planetary science assemble itself, observation by observation. Across Earth's surface, even larger instruments are rising. In the Atacama Desert of Chile, the extremely large telescope is under construction with a primary mirror measuring 128 feet across. When it achieves first light later in this decade, it is expected to examine nearby planetary systems with remarkable clarity, pushing direct imaging closer to Earth-sized worlds, orbiting within habitable zones, and studying the chemistry of their atmospheres. Another vision remains on the drawing board. The proposed Habitable Worlds Observatory is being studied by the National Aeronautics and Space Administration as a mission built for one central purpose: finding Earth-sized planets around Sun-like stars and searching their spectra for combinations of oxygen and methane that could indicate biological activity. It has no confirmed launch date, and its final design remains under development. Even so, it represents the direction many planetary scientists believe the field must travel. Looking back across the past 3 decades reveals a consistent pattern. Each major leap followed the arrival of a new instrument or an entirely new observational technique. Radio timing uncovered planets around a pulsar. Radial velocity measurements exposed the first planet orbiting a sun-like star. The Kepler Space Telescope transformed photometry, the precise measurement of changing starlight, into a survey of extraordinary scale. The James Webb Space Telescope expanded infrared spectroscopy, the study of light divided into its component wavelengths, into an unprecedented exploration of planetary atmospheres. The next discovery that reshapes our understanding will almost certainly emerge from technology already operating or from observatories nearing completion. The iron storms of WASP 76b continue without interruption. The diamond world circling its pulsar remains intact. The exposed core of TOI 849b still follows its relentless orbit. Kepler 78b persists, where earlier theories insisted no rocky planet should survive. Methuselah continues its ancient path after approximately 12.7 billion years. None of these places required our attention to exist. We arrived much later. We became the species that learned how to collect ancient light, separate its colors, and recognize distant worlds from patterns hidden within it. The universe never promised that every question would receive an answer. It has offered something equally remarkable: the chance for each confirmed discovery to widen the boundaries of what can be known. That work is still in its opening chapters,